Hello everyone, welcome to Analog Electronic Circuits, lecture number 19, part number 1. So today we are going to solve a numerical on a cascode amplifier. So let's read the statement. A two-stage circuit is shown below with NMOS enhancement parameters given as Kn1 is equal to Kn2 is equal to 0.8 milliampere per volt square. VTN1 is equal to VTN2, which is the threshold voltage for both the devices is 0.8 volt. We have to calculate the DC parameters of the circuit, input resistance, output resistance, and voltage gain of the circuit. So this is the circuit given to us over here. Okay, so this is the circuit given to us. As you can clearly see, input is applied to the gate terminal of M1 transistor, and the drain terminal of M1 transistor is the output of the first stage, which is driving the second stage input. So first stage is my common source amplifier, and second stage is my common gate amplifier configuration, right? So it's a cascode configuration, CS-CG cascode configuration, right? So let's begin with our solution. So first of all, we'll identify the circuit. We have already done that. Then we carry out the DC analysis. Then we find out the small signal parameters, draw the small signal equivalent circuit, and finally we'll estimate Rn, Rout, and the voltage gain. So let's begin with identifying the circuit. So since we have already done that, the given circuit is common source, common gate, cascode amplifier. Okay, so that is what the circuit is about. I mean, we have identified the circuit successfully. Now let's proceed on with the DC analysis part. So let's have a look at it once, the circuit diagram. So for the DC analysis part, all the connected capacitors will behave as open circuit. So we left out with all the resistors R1, R2, R3, RD and RS, and M1 and M2. That will be it, along with the supply voltage VDD. So let's do that, right? And first of all, let us also identify whether M1 is in which configuration and M2 is in which configuration. So M1 is in common source stage, and M2 along with the capacitors and the resistors will form the common gate stage. So always remember that, don't interchange them so that you don't have any confusion in the formulas. Now let me start with the DC analysis to find all the terminal currents and voltages. So B part is DC analysis of cascode stage, and this cascode stage is CS-CG. Okay, so now we can proceed with the DC analysis part. So for the DC analysis, we have to consider all the connected capacitors to be open circuit. So your DC analysis, DC equivalent circuit will look something like this. So over here we have M2 transistor followed by M1 transistor. Then we have RD resistor over here, RS resistor, R1, R2, and R3 will form the three biasing resistors. Okay, so here I'll connect to the gate terminal, here the gate terminal, and this is the VDD supply. So let me mark it as R1, R2, R3, RD, and RS. Okay, let me maximize a little and scan it a little up so that we can write down the values of current and voltages over here. So let me first write down the terminal names. This is gate 1, drain 1, source 1, gate 2, drain 2, source 2. So as you can easily see, source 2 and drain 1 are tied together, and the various currents in the circuit. Here the current flowing to the gate terminal will be 0. So the IG1 and IG2 will be 0. Then the current flowing through RD register is ID2, which is same as IS2, which is same as ID1, and which is similar to IS1. So all these currents are same. And also, if I want to measure any voltage, this voltage is VG2 DC voltage, and this voltage over here measured with respect to ground. Okay, so don't forget that it is they are measured with respect to ground. So VG1 and VG2, if you want to find out, right? So first of all, over here we can write your current IG1 is approximately equal to Ig2. They are very, very small in nanoamperes, I say. So we'll consider them to be 0. What is the reason for that? The other reason for that is that, let me add it over here. Your MOSFET have, what is the other reason for having gate current to be 0? In a MOSFET, we have the gate isolated from source and drain, okay, with an oxide layer. So since we have an oxide layer, this is metal oxide semiconductor. Oxide layer is isolating the gate from the source and drain. That's why the gate current is 0, right? That's the formal reason for it. And then we can assume that the current ID2 will be equal to the current IS2, which will be equal to the current ID1, which will be equal to the current IS1, right? So all the currents will be equal in the circuit. So all the terminal currents can be easily evaluated if we get one value of current from here. Next is, third is, we'll find the value of VG1 and VG2. So VG1 will be R3 upon R1 plus R2 plus R3 into VDD. So we'll write over here R3 upon R1 plus R2 plus R3 into VDD. Simple voltage division rule. And now we substitute the values over here. So R3 value is given as 12K. Then R1 value is around 100K. R2 value is 24K. R3 is again 12. And VDD value, I guess, it's given as 18 volt. So we have to find the value of VG1. So if you plug in all the values in the calculator, you will get the value of VG1 as equal to 1.588. It's 1.588 volts. Let me highlight it with yellow color. So quickly calculate the value of VG1. Solve it along with me. You should have a habit of doing that now. So now VG2, what is the formula for VG2 if you have forgotten? So if you are not comfortable with any, if you're not following any steps or comfortable with it, we have already discussed this in the previous session. So watch the previous video before you attempt the numerical, right? About the analysis of the cascode amplifier based on MOSFETs. So over here, VG2 will be R2 plus R3 divided by R1 plus R2 plus R3 into VDD. Simple voltage division rule again applied over here. Now we write over here R2 plus R3 divided by R1 plus R2 plus R3. So R1, R2, R3 values are there, 100, 24, 12. R2 plus R3 is 24 plus 12 and into VDD. VDD is 18. So if you solve this in the calculator, let us, this is R2 value, this is R3 value, R1 is 100K, and this is around 18 volt. So if you plug in these values in the calculator, your value of VG2 will be higher compared to VG1, and it's coming out to be 4.764. Okay. So that's the value of VG1. So VG1 and VG2 we have calculated. Next is we have to calculate the value of VGS and ID. So let's proceed forward. So we can write VGS1 is equal to VG1 minus VS1. And what's the value of VS1 from here? VS1 from the diagram. What do you see? Let us check it out. Yeah, so ID1 is same as IS1. So VS1 will be ID1 into RS, right? So we'll write it in that form. Your VS1 will be equal to ID1 into RS. So let me rewrite this formula again, expression again. VG1 is 1.588. So we can write over here VGS1 is equal to 1.588 minus ID1 into RS. And what's the value of RS? The RS value is around 1 kilo ohm, right? So we can rewrite this as, that is VGS1 is equal to 1.588 minus 1K is around 1000. So 1000 times ID1. So this we call it equation number 1, right? Because we have to find two unknown values, ID and VGS, will require two formulas, right? Two equations basically. So next, we assume that the MOSFET M1 is in saturation. In fact, both the transistors should be in saturation. So we can write the drain current expression as ID1 is equal to Kn1 times VGS1 minus VTN1 the whole square, right? And very confidently we can write this so that while assuming M1 transistor, M1 is in saturation. Okay, if M1 is in saturation, we have a drain current ID1, which is also the formula in saturation. Now we have to just, let me just write the values of Kn1. So ID1 will be equal to, Kn1 is 0.8 milli, so 0.8 into 10 raised to minus 3. Then we have VGS1, which is unknown, and VTN is 0.8, right? So let this be equation number 2. Now, if you see carefully, equation number 1 and 2, there are two unknowns and two equations. So we can solve them and get the value of VGS1 and ID1. So now what do? Is we put equation number 2, the value of ID1 in equation number 1. So we can put equation number 2 into equation number 1. So we'll write, we get, now we have to write that VGS1 is equal to, that is VGS1 is equal to 1.588. We are writing this minus 1000 times ID1, and 1000 multiplied by 0.8 milli will be 0.8 only. So minus 0.8 into VGS1 minus 0.8 the whole square. So it will be VGS1 square minus 1.6 VGS1. A square minus a minus b the whole square. It will be a square minus 2ab plus b square. So plus 0.8 square, which will be 0.64, right? So now we open the bracket and solve it. These are mechanical steps now. Not much explanation required over here. So what we do is we rearrange all the terms and we multiply, and finally you will get an quadratic expression in terms of VGS1. So I'll writing the final expression. Intermediate steps you all can complete it. So it will be 0.8 VGS1 the whole square minus 0.28 VGS1 minus 1.076 is equal to 0. So now we will solving quadratically. So you can put these values, put this equation in the calculator. It will directly give you two values of VGS. So after putting in the calculator, you'll get two values of VGS. One value came out to be 1.3478 volt, or other value came out to be VGS is equal to minus 0.9978. So definitely without even looking, we can have to accept this value and reject this value, because the gate to source voltage cannot be negative. It has to be greater than VT. So here we have to write, since VGS1 is greater than VTN1, right? So definitely it's greater, because VTN1 is, I think, 0.8, and 0.8 is greater than, let me write over here, greater than. Yeah. So this value is around 0.8 and this value is around 1.3478. So definitely VGS1 is greater than VTN1, and that's the condition which we are looking for. So this is the value of VGS1. All right. Now we got the value of VGS1. Now we can find the value of ID1. Okay, so this is step number 7. So ID1 will be given by KN1 times VGS1 minus VTN1 the whole square. So over here we have the value of KN1 as 0.8 milli, VGS1 as 1.3478, and VTN given as 0.8, right? So if you substitute all the values over here, you will get the value of ID1 as in the calculator. ID1 is coming out to be 0.24 milliampere. Okay. Now, since ID1 is coming out to be 0.24 milliamperes, all the terminal currents are going to be same, the drain and the source terminal currents. So we can write over here ID1 is equal to ID2, which is equal to IS1, which is equal to IS2, is equal to 0.24 milliamperes, right? Okay, we are remember we have assumed that the gate current is negligibly small, hence we have approximated it to be 0, right? All right. Next, we find out the value of, okay, let me turn on the pen, black color. Next, we can find out the value of VS1. So VS1 is given by ID1 into RS. So ID1 value just now we found out to be 0.24 milli, and RS value is how much? It's 1K. So very straightforward answer, don't even require a calculator over here. So VS1 value is coming out to be 0.24 volt. Okay, so we got the value of VG1, we got the value of VG2, ID1, ID2, IS1, IS2, and VS1. Next, we find the value of VD2. All these things we have discussed last time, right? If you want to, revise it again, you can refer the last video lecture from this topic, 18 point, I think 1. Yeah, I think it was 18 point, this is 19.1, so it was 18.2, right? Analysis of cascode amplifier. So over here, what was the value of VD2? So VD2 will be VDD minus ID2 into RD. All right. So let us calculate that now. So we will calculate the value of VD2 now. Next. So this is point number 9. Okay. So next we find the value of VD2. So VD2 value is VDD minus ID2 into RD, right? Over here, the VDD value is around 18 volts. ID2 value is same as ID1. So its value is around 0.24 milli. And what's the value of RD? So the RD value is around 3.3K. So if you plug in all the values in the calculator, you will definitely get the value of VD2, and its value is around 17.2 volt. So we'll highlight this number, 17.2 volt. Okay. So now that we found the value of, let me go down slightly. Now, since both M1 and M2 are symmetric transistors, let me go back to the circuit now. You see, if you look at the circuit diagram, M1 and M2 have similar parameters. Kn1 and Kn2 are same, VT1 and VTN2 are same. So their VGS1 and VGS2 also will be similar, right? So for if M1 and M2 are symmetric, their VGS values also will match. So let us go down and check it out, how to proceed further. Okay, so next we'll calculate the value of Vs2. So we know that since both are symmetric, both M1 and M2, VGS1 and VGS2 are same, which is equal to VG2 minus VS2, VGS2 actually. And we can write that is Vs2 will be equal to VG2 minus VGS2, right? All right. VG2 value came out to be 4.764, and VGS1 value came out to be, which is equal to VGS2. It is value is 1.3478 volt. All right. So therefore, the value of VS2 is coming out to be 3.416 volt. Okay, that's fine. Very good. Yeah. Now let's again look back at the diagram, DC equivalent circuit. So if you see carefully, let me go slightly up. If you see carefully in this diagram, your source 2 and drain 1 are connected together. So VS2 voltage will be equal to VD1, right? So let's write that down. Yeah. So here we can write it down that VS2 is equal to VD. Okay, VS2 is equal to VD1, which is same as 3.416 volt. Okay, so with this, we have calculated all the terminal voltages and all the terminal currents. So let me add it as a summary over here. The DC parameters. So what were the DC parameters? First of all, we have IG1, which was equal to IG2, which was approximately 0. Then we had ID1 equal to ID2 equal to IS1 equal to IS2, which was equal to 0.24 milliamperes. Is that fine? So that was the value of the drain current and the source current all are equal. Then we found out the value of VG1, and let me check it out. How much was the value again? Your VG1 value was 1.588 volt. Next, we found out the value of VG2. Definitely, it was a higher one. It's 4.764 volt. Okay. Next, we calculated the value of VS1, I guess, right? Yeah. So VS1, which was 0.24 volt. Fine. So we got the value of VG1, VG2, and VS1. Next, we calculated the value of VS2. VS2 came out to be, which was same as VD1, came out to be 3.416 volt. So this was the value of VS2 and VD1. And finally, we also calculated the value of VD2. So VD2 was around 17.2 volt. So these are all the terminal currents and terminal voltage for the given cascode amplifier, which we just now found out. Fine? Fine with it? Yeah. So next is we will find the small signal parameters of the circuit. So let me add over here point number C, small signal parameters of the cascode, common source, common gate, cascode amplifier. So we'll find these parameters one by one. Now, what are the parameters of the circuit for MOSFET? GM1 is twice KN1, VGS1 minus VTN1. Now, since both M1 and M2 have same parameters, your VGS1 and VGS2 are same. So therefore, your value of GM1 and GM2 will be same, right? So here the value of Kn is around 0.8 milli. The value of VGS1 came out to be 1.3478, and VTN1 is 0.8. Sorry, very sorry, your square term is not at all coming. There is no square term over here. Okay. So remember that for GM, there is no square term. How can we see, how can we make sure our formula is correct? Let me show you a quick technique to check the formula. So what is the drain current formula in case of MOSFET? Kn times VGS minus VTN the whole square, right? If you want to calculate GM is what? Delta ID upon delta VGS. So we have to differentiate this expression with respect to VGS. So what do we get? We get delta ID upon delta VGS, and here this 2 will come out and you'll get twice Kn VGS minus VTH. Okay, so that's how we got the expression of GM, and this is nothing but the value of GM itself. So sometimes it get confused in the moment. You can just substitute as twice and everything will go wrong. So be very, very careful around this, simple mistakes. So finally, if you substitute all the values, you will get GM1 as 0.876 milliampere per volt. Okay. And this value of GM will match with the GM2 value also, because both the transistors are symmetric, right? So this is also equal to GM2. All right, let's move on further. And what's the reason for that? What is the reason for this? Both M1 and M2 transistors are identical. Both M1 and M2 transistors are identical. That's why we can write GM1 and GM2 are similar. Next, since lambda 1, lambda 2 values are not given, we will assume RO1 equal to RO2 equal to infinity. Okay. Always if the value of lambda is not given for MOSFET, and or the value of RO1 and RO2 are not given, safely assume it to be infinite. All right. Next, after this, ideally we should be calculating R in, R out, and AV. And for that, you have to draw the mid frequency small signal equivalent circuit. Mixed frequency small signal equivalent circuit. Okay. Actually, this mid frequency small signal equivalent circuit we have already covered in the last lecture, but still I will show it to you, a glimpse of it from the last lecture itself, so that we can directly continue. So here, I can write, instead of drawing it again, kindly refer AEC handout 18.2 for this drawing the small signal equivalent circuit, mid frequency, and also the formulas. Right. Now let me go back to that handout of 18.1. I think it was 18.2. Okay, here it is. So here I'll directly analyze the circuit and we'll directly write down the formulas for uh, you know R in, R out, and voltage gain. So this was the mid frequency small signal equivalent circuit for the same cascode amplifier. Only addition over here is that RL is not present in a present numerical. So if RL is not present, you have to keep it as open. I mean, that will be open and RL will not be present in parallel. So Rn formula will be same. It will be R2 parallel to R3. R out formula, that will be equal to Rd itself, because in the numerical, the value of RL is not given. And then we can find the value of voltage gain. So the second stage voltage gain formula will be GM2 into Rd parallel to RL, but RL is not there, so it will be GM2 Rd. And in the first stage, you have the value of voltage gain as -1 directly, right? No need to derive these things. So now let us go back to the numerical and complete the remaining part. Okay, so yeah, let me go back to the point where I have left. It was mid frequency small signal equivalent circuit. Okay, let me reach up till here. Okay, fine. So here, without drawing the, just now we have referred the mid frequency small signal equivalent circuit. From there, we can write Rn is equal to R2 parallel to R3. So what's the value of R2? I think it's 24K and R3 is 12K. Okay, so if you substitute in the calculator, if you solve it, you should get the value of Rn as 8 kilo ohm. Let me highlight it. So the value of Rn is coming out to be 8 kilo ohm. Next, we find out the value of R out, and that is just equal to, that will be just equal to Rd. I think an Rd value is, I think 3.3, yeah, 3.3 kilo ohms. Let me highlight this also. This we have just now seen in the few moments ago from the last session. Now we have to calculate the voltage gain AV2. So here this was first, second, and this will be the third point. Okay, so AV2 will be, uh, you know, the formula was GM2 into RD. So what was the value of GM2? It is 0.876 milli, and the RD value is 3.3 K. So if you plug in all the values in the calculator, you will definitely get the value of AV2 as, what was it was coming, plus 2.89. Okay, remember in this case the second stage gain is positive. Okay, next, once we found out the value of AV2, we'll turn our attention for AV1, and AV1 it's directly equal to -1. That's what we have seen last time also. So let me highlight this point. Remember, AV2 is the gain of the next second stage. AV2 is the gain of first stage. What about AV1? AV1 is the gain of, okay, sorry, I did a mistake over there. It's not a gain of second stage. Over here, it is gain of second stage, AV2, and AV1 is the gain of first stage. And yeah, so the total voltage gain will be, let me add it out. So your overall voltage gain will be AV1 into AV2. So over here, AV1 is -1 and AV2 is 2.89. So the overall voltage gain of a cascode amplifier for the given numerical will be -2.89. Okay, so this is my overall voltage gain for the given circuit. It's -2.89. I think with this, we completed the numerical. We have successfully calculated the values of, you know, the DC parameters of the circuit, all the terminal currents and voltages. Then we found out the value of Rn, R out, and finally we calculated the value of voltage gain. So with this, we come to the end of this numerical, and I think next time we will start with a new topic. So yeah, that's it for today. See you all next time. Have a good day, and thank you for joining.